Tuesday, you'll see when you start moving the parts next to each other, and it won't allow you to do so, even though you can still place it in the view, layout view. But the thing is, there will be a little indicator saying that it's error. Okay, so which means it's violating the design rules. So what are design rules? So it's basically defining the spaces between different traces within the same layer, like metal 1 to metal 1. If you place them too close to each other, actually the fabs manufacturing process, or that technology process, like 500 nanometers, is now able to resolve it. So now able to resolve that gap. Then you have to place them a little bit apart away from each other. So that's the design rule. But do you have to remember all the design rules? No, because that software will do that for you. Okay, and a lot of times you place them even though you see there's no design rule violations marked in your layout. But if you run DRC, design rule check, right? So it's gonna show you how many errors you have, and then you can go through every single error and fix all these things. And I saw one little error from last week from a student. I think that was Kevin. That's brought up a really interesting thing, and a lot of people probably didn't know. So I think that's a good example. Even though, for example, these are both metal ones, right? So metal 1. And there's a certain gap you need to maintain. However, you can make turns, because a lot of times you are making connections and requires you to have a turning. It's turning to the other side and make connections. So this little gap here, sometimes it's too small. It won't be able to resolve it. Okay, be careful about that part. If it's marking a DRC error violation here, you need to know that some of the very small turns cannot be resolved. So you have to make this longer probably, or yeah, things like this. And another example is really interesting. Probably if you haven't experienced this yet, you probably don't know what's really happening. You got a metal 1 wire here, okay, metal 1, and you got another metal 1 wire which has a different width. And you are trying to make a connection. They have different width of the traces, and then it shows a DRC violation. What's the problem? That's what I'm talking about. The little turn here. So this little part cannot be resolved. I mean, the fab doesn't know this doesn't matter, but the thing is, it's going to report an error. You know it doesn't matter because it's just metal, even though it's not being resolved. So the fab probably will eventually give you something like this. But the tool doesn't know that. The tool feels really bad about itself. It feels like it didn't do whatever you require the tool to do, right? It eventually cannot resolve this corner, but it's actually it's a bad design. It's on you. So something like this you're going to avoid. Whenever you are laying out traces, make sure they match. If they don't match, maybe try to push this one a little bit to the side, so at least one set matches, and you are giving like this. You can give an overlap, so it's making a connection, and you are giving a bigger corner here, right? So it's able to resolve it. It's another problem you need to know. So the design rules not just for metals, but for all different kinds of corners. For example, I have a metal 1 and connects to a via. The via is usually a little bit bigger. It's a metal 1 to metal 2 via, for example. And the metal 2, here's the metal 2. And you can imagine this is from the top, but the thing is, if you look at from the side, the metal 1 at the bottom, drill a hole to the top, and metal 2, right, like this. And metal 2 to metal 2, there will be a design rule, the gap. And you have a metal 1 to metal 1, there will be a gap, defines everything. And also so quick question here. For this component, this is something available in the library, okay, this component. So does this component have both metal 1 and metal 2 on the top overlay? So like metal 1 at the bottom and metal 2 on the top? It should. So it's shown a purple color because it has not really purple, but like blue and purple mixed. I forgot what the color is, but this is light blue, this is purple, and you put them together, it shows a different color because that's a metal 1 to metal. It has both layers in there. So in that case, if you left click, for example, you grab this node without anything else, without a metal wire, you just grab this thing, It has this outline and has a little via in the middle, right? It's from the library. So the tool did it for you, okay? And then you select metal one. You left click in the library, select the metal one. So you left click first. This is step one, left click. And you select, in the library, you have all different components. You select the metal one, right? Metal one, the light blue color. And then you right click in the space, empty space here. So it's going to introduce the metal one for you, okay? So same piece of library component like this one, you left click, and then you go to the library, left click the metal tool component. So select the metal tool, and then you right click, it's going to introduce the metal tool. So depending on which one you select in the library. So this node can introduce both metals because it has both metals on the top of each other for this component, depending on which one you select in the library. It's just a left click and right click. So right click is placing a wire, left click is selecting something. Make sense? Okay. Any questions on this by far? Okay. And another thing, so for Metal 3, and there's a really interesting lab towards the end of semester, and I'm gonna have you guys to do a manual wire bonding. So it's all these layers, I'm just not drawing them. But for Metal 3, here's Metal 3. How do we make a connection to the outside world? How? It's all insulation layer on the top. But actually the top insulation layer is a bit thicker. They call it passivation layer. Passivation. Can't spell. Can't spell really well with anything. Anyway, you know how to pronounce it. Passivation layer. Passivation layer. I'm sure I spelled it wrong, but so passivation layer is also insulation layer, and there's a component in electrical VLSI in the library, and you place on the top of Metal 3, and it's gonna open up. It's gonna open up this guy. It's gonna open up the passivation. So this will be removed during the fabrication process. So it's gonna be opening on Metal 3. And then you place this one in the package, like I showed you all the chips, right? Including all the Arduino chips, the same thing, it's a different package. So usually what we have is the DIP 40. Has 20 pins on each side, so it's total 40 pins. The very fundamental prototyping packages, and you can place your die in here, and these are all the pads around the chip, and every pad has an opening. It's a Metal 3 has an opening on the top. Then you do these connections, right? So they have another package here, do the connection to the pads. That's how you do it with the wire bonder. $25,000 device I purchased 7 years ago. Okay, and it's still functioning, but we just damaged the tip in the summer, and I ordering another one from Germany. It's coming, I hope. I ordered in May. It's still not here yet. I feel like all these places, they hate you. The salespeople just hate you. Whoever buying anything from them, they hate you. I don't know why. I call them so many times. Sometimes they don't pick up the phone. Sometimes they tell me it's not available. And I mean, you guys are selling something to me, right? Why you hate me? It takes so long. Hopefully it will arrive before the end of semester, so you guys will get your experience on wire bonding something, and this will be very unique. Trust me, this is really good experience to have. So do I have an example for you? I do, but let me see if I can find it. I just saw it, but I closed that. Much time on this, but just want to let you know how the wire bonding works. So you can see this is a chip. So these are the little pads. These little tiny dots are the Metal 3 pads with the opening on the top. Okay, and you have Metal 2, Metal 1 down below that, and short to the circuits in the chip. And this is 1.5 by 1.5 millimeter is under the microscope, and that's the package's bigger pads. And you are making connections from these little Metal 3 pads to these bigger pads, and eventually these are shorted to the pins of the packages, the 20 pins on each side. Okay, and how to bond it? This is the tip, and you have very thin gold wire going through this tip, and it's not heating up actually. So what this does is, because the gold wire is super thin, and it just push really hard onto the pads and smear it on the top. It doesn't like soldering, you have to heat it up. Because they are super thin and the metal is kind of soft down to that scale. So it's basically just this tip, and when you bond it, give a pressure on the top and just smear that gold wire onto these pads. You can see these little dots are smeared wire, connection joints. You couldn't see the wire because they are so thin, right? And the way to bond it, the process of bonding is like this. You see the wires? Okay. So that's a metal 3 opening to the pads in the package. Everyone will get a chance to do it if the Germans really ship to me by the end of this. Please be nice to us.
So, like, because you're not like heating or like chemically bonding it, wouldn't there be like an issue with like contact, or is it like just because you're literally pressing it together, it's like borderline just melting the two?
Yeah, I think it's just I haven't seen any issues with that. So it's what that is doing is giving a pressure and also passing an ultrasonic like vibrations through that wire. But I don't think that really helps the solder the connection. I think the ultrasonic signal is just give a little vibration so the wire can go through the tip really smoothly. It's not stucking into the capillary space inside. But what really solder or make the connection is just the pressure. Very interesting, right? Yeah. Okay. So that's the metal 3 connections and design rules and vias. Okay, vias. You'll see sometimes metal 2, metal 1. And when you make this bigger, and they will, by default, they will just directly create more vias for you instead of just one. Why that? Why not just one big via, but 4 individual vias? So if you look at the connections, metal 2 wire, metal 2, and every via has a certain resistance, even though it's a metal, right? But again, if you model the circuit, it looks like this. So these are the vias. Very low resistance though. I mean, 5 ohms or so. Very low metal. Even lower, probably lower than that.
I guess because the parallel resistance would be less than.
Yeah, first the parallel resistance will be smaller.
Yeah.
Good.
And because if you just have a larger visa, it would have like, I guess the entire resistance would be greater than that parallel resistance, I guess.
Mm-hmm. Yeah. And in addition to that, you are getting some backup vias. So during the process, if some of the vias failed, and you still have backup vias to make the connection, so it will increase the yield. Keep in mind, in semiconductor industry, yield is very important. Whoever has a higher yield, even 1%, will win the entire industry or the entire market. It's very simple math. You know, TSMC can fabricate 28 nanometer at a 98% yield, which means on the wafer, you have the wafer here, and after the fabrication and testing, you find out 98% of the chips are working. But another foundry, for example, have 95 instead of 98. And all the customers will directly order from TSMC instead of the other one, right? It's a very simple theory in the semiconductor industry. Very cruel, but very brutal, but it's how that works. So yield is super important. For 180, which is 20-year-old technology we are going to use, it's almost 100% yield. It's very mature technology. So the winner take over the whole market. So in that case, you have more. There are so many other details that the foundries are using to increase the yield, but making different vias is one of them. It's a really simple one to implement into your design. And the electric VLSI, the tool will directly create all these vias for you. You don't have to manually do it. It's actually doing that. So it's checking the area of the overlapping area of metal 1 and metal 2 or other metal layers. So whenever this area increases to a certain level, the calculation that passes that threshold is going to start adding more vias to it automatically. You don't have to manually do it. Okay. Any questions on this? Cool. Simple things, right? And another thing you need to know which is the poly resistors. You know, the poly layer can be used as resistors and capacitors. How to use the poly layer as a resistor? So you have poly as a fox, for example, and here's poly. Let's just draw a poly here. Okay, that's a poly. That's fox. It's poly. And if you want to reduce the resistance of the poly, what you can do is you can coat a more conductive layer on the top, and that's called silicide. Silicide. It's killing the resistance of that polysilicon, but I mean it's called silicide. So in that case, if you have wires, and it's actually directly making a contact to the metal layer, metal coating on the top, instead of directly connecting to the poly. So in that case, you can do all the wiring in metal one, and if you're trying to use a lower resistance for the poly. But if you don't need a lower resistance, if you just directly want to use a polysilicon as a resistor, so don't coat it. Don't coat this silicide layer on the top. And typical numbers for the resistance compared to metal. So this is about 200 ohms without silicide, okay? 200 ohms per square. That's the sheet resistance for poly. Remember the NWL sheet resistance was 800, about 800 ohms. So if you need a less resistance, use poly. If you need a more resistance, use NWLs. Metal is about 0.1 ohms per square. So you don't really use metal as resistors. That's crazy. But you need to know that metal also has resistance. So here's a really important tip when you do the layouts. Okay, let me show you one example here, not this one. This one. You'll see this a lot when you are doing the layout. So take this as an example. I don't know if this is a good example, but probably this one probably. Okay, you see? Sometimes I don't have space for making a via here and go to metal one, then connect to another poly, because if I, for example, I do need a connection between these two polys, these two gates, and there are multiple ways to make the connection. You can directly place the via here and go to metal one, then metal one like a bridge, right, and go here and go down by one more level, down to poly again with a via, and then come to this poly. But the thing is, you don't have space, so you got a metal one immediately after next to it, and if you put a via here, it's gonna have a DRC error. So in that case, you just have to use a poly to make the connection. But the thing is, if a poly to make a connection, what's the problem? It has resistance between the gates, and there will be a voltage drop, right? So in that case, it's not ideal. But the thing is, it's super short. It's probably fine. I'll just directly use poly to make the connection. Like this case, okay? This case. I know this is not ideal. There must be other ways to make the connections. So there is poly connections between the gates here, and I won't be able to have any space to connect this one to here by going down from this location. So I have to route it this way. So it's not really ideal. I just did it. But if you want to really reduce the resistance, there's no space to place the via here, but you do have space to place the via here and use this part as a metal one, right? And then you drill a hole down to poly, and then you can eventually reach here, use a poly. So I didn't do that, but I just telling you that's another option since you have space. If you don't have space, I just use poly. But try to avoid long poly wires. For example, here. Okay, see, I got a poly here, and I want to, once I have some space, I want to directly drill a hole to metal, and then make the connections through. I don't want to poly directly go to this point and then drill a hole to metal. It's introduced too much resistance. Once you have space, you want to drill a hole and get rid of putting too much poly in there. Okay, similar to here. You don't have space because you can see poly goes up, and all these are the well taps. We'll introduce that concept later, and there won't be any space to place a via. And until here, you got a space, but it's already reaching the destination. So I'll just directly use poly. Make sense? So poly has resistance, higher resistance. So when you are laying out, keep that in mind. It's introducing resistance. Okay. And poly can also serve as capacitors. I'm not drawing Fox, just directly. Oh, let's draw it. Better practice. It's metal one. It's poly. It's Fox. So poly one, you have two poly layers. Keep in mind, poly one, make it a poly two, and you can drill holes, make a via from poly two to metal one. You can also drill a hole, make a via from poly one to metal one. And here's metal one, and this is also metal one. I can drill holes to metal two and eventually introduce the wires to the metal three opening and to the wire bonder. So what is this doing? It's forming a cap. You can see poly one and poly two, even though they are in the same poly layer, but they are actually separated by the insulator layer. Okay. So that's going to be the material between these two poly plates. That's a cross-sectional view, but from the top you can imagine they are going to be a square or something, right? It's a block. So there will be an overlapping area, and we know that capacitance equals epsilon A over D. So that's the area, overlapping area. And that's the distance between the two plates. And that's the insulator's epsilon, the dielectric materials, a dielectric constant, I think. So that's not changing, determined by the process. And you can the distance is not changing because the P1 and P2 they are being manufactured at a certain location, within that layer, and you cannot change it. That's a different process. Will do that automatically. So the only thing you can change the area. So when you are doing the layout, you manipulate that overlapping area to change the capacitance. So there will be a parameter is telling you the sheet capacitance. Okay, so there will be a parameter table you can look up, right? So there's a 10 micron by 10 microns giving you like several hundred picofarads. So you can use that one, and you can consider multiples of that area in order to generate various of amount of capacitance from that overlapping area. Okay. Can you imagine this is two plates and two connectors? So it's a forming capacitor in the middle. That's how that works. And there are also, remember, we introduced the parasitic capacitance between the diffusion layers, and you can imagine this is a p-type. And these substrates are actually shorted to ground. So if you consider the ground is another metal connection, and there are parasitic capacitance between this to this, and also this to metal 1 to metal 2, whatever. They are just all of these existing physical capacitance undesired. Okay, so sometimes they introduce errors, and the most significant one is poly 1 to to sub, to the substrate. Parasitic capacitance. No, nothing fancy, just keep that in mind. So you know that there are undesired capacitance existing.
So that's like the largest parasitic capacitance?
Yeah, that's the most significant, the largest contribution. Largest undesired.
Is the design software like? Does it have any design rules that warn you about that? Like if you.
Yeah, the tools can. I mean, in electric VLSI, we just ignore it. I don't think we are really caring about that. But in cadence, whenever you are using some smaller capacitance, there's usually 50% of the time of the design period is about timing. So all these parasitics will contribute to the timing, the delay, and giving errors. So you are not fixing individual ones. You're just after the design, you run that timing and see if the certain nodes are reaching the required timing. If not, then you come back and optimize it. But you are not. There's no way that I can fix individual ones. And usually for digital design, VLSI design, 50% of the time of the design period is on timing. So you design the RTL from the front end designer and convert it into layout, and then the rest of the time is just for timing.
And the software can't just include like parasitic. You can't like predict the.
They do. That's why
capacitance.
it's reporting you the timing, because it's able to detect that, even though it's not super accurate sometimes. But that's why the cadence tools are so expensive, because they can do all this analysis, and all the open source tools cannot. That's another interesting to talk about. There are a lot of efforts. So MOSFET, and people are talking about, is this a MOSFET or MOSFET? It's actually MOS. It's MOS, not MOS. No, MOS. So keep your mouth small. MOS, okay? It's not MOS. It's MOSFET. So it is metal oxide semiconductor field effect transistor. So these are transistors, MOSFET transistors. And there are different two major types of MOSFETs, and one is called NMOS, N-type. One is called PMOS, and you are going to deal with all these NMOS and PMOS for the rest of the semester daily. So it's N-type, it's a P-type. N-type and P-type. So we will introduce N-type, and it will be very similar way to operate for the PMOS. PMOS, not NMOS, NMOS, PMOS. Symbols. Here is the NMOS. Here's the PMOS. Cross-sectional view for NMOS. Now here's a poly gate. Now here's a P+. It's called a well tap. It's important to understand what well tap does. This is a well tap. Why it's called well tap? It's a P sub, right? So for NMOSes, NMOSes are being put in P well. everything. There's no POL, it's a P sub. Depending on different processes, right? There will be double well processes, but we, in general, we just call the P sub a POL, even though it's not a POL. It's a big well. It's actually the wafer itself. So we call it POL. So NMOS is being manufactured in the POL, and PMOSes are being put in the NWEL. Let's start with the NMOS first. NMOS is in POL, which is the P sub, and we do need a connection between the P sub because all the P sub are shorted to ground. So I'm gonna let you know why very quick. But why P subs are shorted to ground? Because we want to avoid something we undesired, right? It's called body effect, which increases the threshold voltage of the NMOS. Oh, so many new terms, which is fine. We'll get into that later. But now you need to know that P sub need a P plus as a well tap. No matter what kind of technology they are going to use, it's either next to the transistor or it's in the row at the end of the row of the chip. You'll see that with cadence later, but it's called a tapless. Jesus, I forgot the term. Probably tapless. So it's called tapless process, which can get rid of the well tap next to the transistor. Why? Because you can think about that in older processes, they require the well tap next to each transistor. It's introducing a little extra area for every transistor. You have billions of transistors. It's a huge area waste. So they are trying to just do the well tap at the end of the row for every single row. But now, why do we need a P-type? Come back to this topic. So P-tap means it's like tapping, right? Tapping. It's a P-type material as a wafer, and P plus is just a more heavily doped P. But the sub is also P, but it's lighter, it's lightly doped. It's less conductive. But the P plus is heavily doped P. It's more conductive. So this is eventually shorted to ground, and that's how we short the P sub to ground. And you're thinking the wafer, I have a wafer, here's the bottom of the wafer. Why not just directly short, put a wire here, whatever, you put a metal piece and ground it? It's at the bottom, how to ground it? It's at the bottom, and silicon is not really conductive. So it's not a very good way to short it to ground. So how to short it to ground? Have a more conductive little piece here, and just implant it into the general P. So it's making a connection here, and then you short this one on the top. How to short this one to ground? You have all the metal layers, and eventually go to metal 3 has an opening and short to ground. Okay, or you can have this wire go to metal 1, you connect to the universal ground circuit, but not at the bottom. There's no way you can put a wire at the bottom of the wafer and short the ground. But a lot of times you see the symbols and drawings in different textbooks. They directly show you, but this is just a concept. It shows you the P sub is short to ground, just concept. It's not physically doing that. Why we are doing that? Why we are shorting P sub to ground? Because see here, when we are operating this NMOS transistor, the way we do that is first we connect a voltage source, the gate voltage, and we short this pin to the well tap, the P tap. So this is the gate terminal, the source terminal. It's detecting the difference between the gate and source voltage. So if you apply a positive voltage at the gate, what's going to happen is, even though it's a P sub has minority that have free electrons, so the electrons will be absorbed, will be attracted to the channel here. It's forming a channel. These are electron channels. So this is basically electrons are coming up because of the electric field. It's forming a layer of electrons. And that's called the channel. It's forming a channel by applying a voltage here. And basically we are looking at VGS. So how VGS, it's VGS from gate to source voltage. And that voltage is going to attract a electron layer over here. And then if you add another voltage here, VDS to the VDS, if you add another voltage here, I name it VDS because that's the drain. This terminal is called drain, as this terminal is called the source. And you're adding a voltage drop between the two terminals, so it's going to run current in that way. But physically, if the current, because that's a voltage drop, right? It's a directional voltage drop. The current runs that way. However, we all know that if the current goes that way, it's physically electrons going the opposite way. Okay? If the electrons are going to the opposite way, it's actually draining electrons in this direction. That's why it's called drain. And it seems like this is the source of the electrons. That's why it's called the source. That make sense? And that's a gate because if you don't turn it on, there won't be an electron layer and there won't be any current going through even though you apply voltage from drain to source. So that's why it's called a gate. The gate turns it on and then you apply pressure here to run electrons to the drain. So it's draining electrons from the channel. Make sense? Okay. So we do need here be shorted to the ground because you can see that it's a P sub and it's an N plus because the NMOS is N plus. It's a heavily doped N type, and there is a what? There is a diode. It's a P junction because that's a P. That's an N, right? So it's forming a little P junction. It's a diode. So sometimes if you accidentally got the P sub has a little bit higher voltage than N, what's going to happen is the diode will be forward biased. You're getting a plus and minus voltage across a diode. What's going to happen? Do you need this diode? It's undesired. Since you put a P plus in the N plus in the P well, so it just forms a P junction there. It's a diode. And if you don't ground your P sub and accidentally your ground has a little bit higher voltage than your N plus, what's going to happen is current is going to run from here to the channel. And that's going to cause what? So if you're injecting current into the channel, you're actually doing what?
I guess you'd like shrink the channel, wouldn't you? Because there'd be less of an electric field. Because they're basically counteracting each other.
Yeah, if I'm injecting current to the channel, it's physically doing what? It's physically extracting electrons from it. Because the electrons flow in the opposite way. So it seems like I'm injecting something, actually you're taking out something from the channel, right? Physically. So electrons are going away, and you are getting a thicker or thinner channel. This is a question, I'm sorry. It's a question. You guys, it's a question. Thinner or thicker?
You get thinner.
Thinner. So physically the channel is getting thinner because this guy is throwing electrons from it. And then if you want to turn it on, you want to keep it on, you need a higher VGS. You know what I mean? So you already put a VGS is good enough, and then accidentally you got a forward biased diode, undesired in there, and then you need a more VGS to keep the channel at a decent thickness to keep it on, right? So which is actually increasing the threshold voltage of turning on this transistor. And that's called body effect. That's called body effect. It's not a definition that I'm going to write it on the paper and let you guys memorize it. It's entirely a description of what's really happening over there. You need to understand what's going on. Critical, okay? It could happen during the interview. If you got a job with Micron, they probably will ask it. What is body effect? It's not a simple answer. You have to show them. But you can make a simple answer if they just desire a simple answer. You can just say, it's because you got a forward biased diode from the sub to N plus, right? And which increases the threshold voltage to turn on the NMOS transistor. So you need a higher VGS to turn it on. And that's the body effect. So how do we avoid that? In most of the cases, we can avoid it by shorting your P sub to ground through this well tap. So that's why we are doing that. Make sure your P sub is always at the lowest potential of the entire circuit by shorting it to ground. If you don't have negative voltages, that will work. If you have negative voltages, you need to short that negative voltage to P to the sub. You know what I mean? So your P sub should always be shorted to what? To the lowest potential of the circuit. Because you never want to forward bias the diode. So the P terminal of the diode should be always the lowest. So you never forward bias it. There won't be any current going through, getting into the P terminal. That makes sense? So by doing this, you are not just shorting the P sub to ground, but also you are shorting the source to P. And so because this P plus is basically this P sub, right? Since I'm just having the heavy dope, so having a better conductivity, I can have a whatever metal or V on the top can make a good connection. But it's basically this P sub. So I'm after shorting this, imagine, I'm shorting the two terminals of the diode. You're shorting the two terminals.
My brains are not.
Any questions by far?
I guess,
So no quiz today, but yeah, any questions?
I guess like for like I guess this is kind of jumping ahead a little bit, but a PMOS would be like inversed, right? Because you'd have to like basically ground different parts of it, right? Because it has different physics.
But usually we just ground the P sub because
I meant like the PMOS, like if you do a PMOS.
oh PMOS.
Yeah.
So PMOS, yeah, good question though. And but any question on NMOS? Any question on NMOS? You got to know this deeply, okay? Got to know this very well. Fundamentals. PMOS. PMOS need to be in well. PMOS. So PMOSs are being placed in the N well, NMOSs are being placed in the P well or P sub. So you add a negative voltage between the source and gate. And it's going to attract the holes from the N type. So holes are coming up. But just the concept, you know that holes are not moving, right? So it's basically electrons are being expelled from the channel, and which seems like the holes are moving. So the holes, we just treat it as the holes are being attracted to the channel and forming a channel of holes, right? And then we add it's VSD. It's just a conversion. We call it source, sometimes call it drain. They are, for the C5 technology, they are symmetrical. It doesn't matter which is which. You just treat one as a source, the other one becomes the drain. So in that case, we call this, we add a voltage source here. We call it VSD because that's a voltage drop from source to drain. So after you turn on the channel by a negative voltage, and you're forming a layer of holes, and then you apply a positive voltage here, and then it's going to expel holes from this source terminal. So the holes are moving in that direction by concept. It's basically electrons are going this direction. Okay. So it seems like that's a drain of holes, that's a source of holes. Okay. Same concept. It's forming undesired diodes here. And if this accidentally becomes a higher voltage, it's going to conduct current. So that running current into the N well from the channel, and what's going to happen is stealing holes from it. So holes are going here, in concept, right? So you are losing holes. Are losing holes, the channel becomes thinner, so the more negative voltage to keep up decent thickness of the holes to form a good channel here to turn it on, keep it on. So in that case, what you want to do here, you never want to forward bias it. So this one is a little bit different, but the PMOS goes, the current goes this way, and here's a higher voltage, and usually you just ground here, so current find a place to go, and you tie this to VDD. So which is being tied to VDD? Unwell. So in our design, we don't have exceptions. We always tie unwell to VDD and P-well or P-stop to ground. So unwell, which is N+, heavily doped N-type material, directly being implanted into the unwell, so it's making a good connection. And then we use all the vias and eventually get a metal on the top of the heavily doped N+ node, and we short this node to VDD. So in that case, the cathode of the diode is always has a higher potential, so you never forward bias the diode. Same thing, to avoid body effect for the PMOS. So keep that in mind. You'll see the well taps in all different designs. They have all different names. In our electric VLSI, I think they are called unwell. No. Forgot. It's just these guys. So keep in mind, we placed all the PMOSes on the top, all the NMOSes at the bottom. So it's called CMOS. CMOS technology because of the complementary MOSFETs, and it's PMOS and NMOS complementary. So in the 40 years ago, people used just NMOS to form logic by putting a resistor on the top. It's pulling up the drain to higher voltage to form logics. It's doable, but taking a lot of space. Imagine you don't have PMOSes, but all the unwell resistors on the top. Something you don't have to know, but we'll get into more details later. But you can see these are PMOSes, and these are unwells, and these are all the P-well taps, P-taps. It's tapping the P. Oh, sorry. PMOS are in the unwell. So these are unwells, and these are the N-taps. So N-taps has N+ in the unwell. Okay, so dots are unwells, and these are N+ nodes with the vias to metal 1. So you can see they are connected to metal 1. So basically an N-tap with metal 1 via to metal 1. All right, we'll talk more about it on Monday. Don't worry about that. It takes time to absorb it.